So we're going to talk about what is normal in statistics. So suppose a friend is pregnant and due to give birth on June 30th. Would you advise her to schedule an important business meeting for June 16th, 2 weeks before the due date? Answering this question requires knowing whether the baby is likely to arrive more than 14 days before the due date. For that, we need to examine data concerning due dates and actual birth dates. So below is a histogram for a distribution of 300 natural births at Providence Memorial Hospital. The data are hypothetical, but are based on how births would be distributed without medical intervention. The horizontal axis shows how many days before or after the due date a baby was born. Negative numbers represent births prior to the due date. 0 represents a birth on the due date, and positive numbers represent births after the due date. The left vertical axis shows the numbers of births for each 4-day bin. For example, the frequency of 35 for the highest bar corresponds to the bin from -2 days to +2 days. It shows that out of the 300 total births in the sample, 35 births occurred within 2 days of the due date, so 2 days before and 2 days after. To answer our question about whether a birth is likely to occur more than 14 days early, it is more useful to look at the relative frequencies. Recall that the relative frequency of any data value is its frequency divided by the total number of data values. The figure shows relative frequencies on the right vertical axis. For example, the bin for -14 days to -10 days, shaded in the dark blue, has a relative frequency of about 0.07 or 7%. That is about 7% of the 300 births occurred between 14 days and 10 days before the due date. We can find the proportion of births that occurred more than 14 days before the due date simply by adding the relative frequencies for the bins to the left of -14. You can measure the graph to confirm that these bins have a total relative frequency of about 0.21, which means that about 21% of the births in the data set occurred more than 14 days before the due date. Based on these data, your friend has about a 1 in 5 chance of her baby being born on or before the date of the business meeting. If the meeting is important, it might be good to schedule it earlier. So the distribution of birth data has a fairly distinctive shape, which is easier to see if we overlay the histogram with a smooth curve. For our present purposes, the shape of the smooth distribution has 3 very important characteristics. The distribution is single-peaked, its mode or the most common birth date is the due date, and the distribution is symmetric around its single peak, which means it goes up on one side, down the other, and about the same thing because it is a bell curve shape. Therefore, its median and mean are the same as its mode. The median is the due date because equal numbers of births occur before and after this date. The mean is also the due date because for every birth before the due date, there is a birth the same number of days after the due date. The distribution is spread out in a way that makes it resemble the shape of a bell, so we call it a bell-shaped distribution. The smooth distribution in the figure with these 3 characteristics is called a normal distribution. All normal distributions have the same characteristic bell shape, but they can differ in their mean and in their variation. The figure shows 2 different normal distributions. Both have the same mean of 75, but the distribution in the first figure has greater variation. As we'll discuss in the next section, knowing the standard deviation of a normal distribution tells us everything we need to know about its variation. Therefore, a normal distribution can be fully described with just 2 numbers, its mean and its standard deviation. So here we can see the two graphs. So the normal distribution is a symmetric bell-shaped distribution with a single peak, and we can see that it's looking that way. The peak corresponds to the mean, median, and mode of the distribution. The variation of the distribution can be characterized by its standard deviation. So if you look here, these both have the same with the 75, but the shape is slightly different. So the frequency changes, but it still has the same mean, median, and mode. But this will have a larger standard deviation, and this will have a smaller standard deviation. Because this is spread out more across here, it's wider, it's going to have a larger standard deviation because more of your data points are stretched out. Where this has more of your standard deviation is going to, or more of your data points are right in the middle. So a lot of them are going to be right here near the mean. Example 1. The figure shows two distributions. A famous data set of the chest sizes of 5,738 Scottish militiamen collected in about 1846, and the distribution of the population densities of the 50 states. Is either distribution a normal distribution? And let's talk about that. So here, this has the bell-shaped curve. If we drew a bell shape on it, we can see that normal distribution, but this does not. So the distribution in figure A is nearly symmetric with a mean between 39 and 40 inches. The values far from the mean are less common, and the shape of the distribution is approximately a bell shape. So the distribution is approximately a normal distribution. But in B, shows that most states have population densities, but a few have much higher densities. This fact makes the distribution right skewed, so it is not a normal distribution. So when it's right skewed, it goes off to the right. Recall that the total relative frequency for any data set must equal 1 or 100. Now consider the smooth curve for the normal distribution in the figure. Although we no longer show individual bars, we can still associate the height of the normal curve with the relative frequency. The fact that the relative frequencies must sum to 1 becomes the condition that the area under the normal curve must be 1. So, the area under the curve must be 1. So whenever you see that, it's going to be 1 because that's what it has to be. So the key idea is this: the relative frequency for any range of data values is the area under the curve covering that range of values. For example, a precise calculation shows that the shaded region to the left of negative 14 days in the figure represents about 18% of the total area under the curve. Now, we haven't learned how to do that precise calculation yet, but we will soon. So we're looking at this part right here is about 18%. We therefore conclude that the relative frequency is about 0.18 for data values less than negative 14 days, which means that about 18% of births are more than 14 days early. Similarly, the shaded region to the right of 18 days represents about 12%. So we're talking about this part right here of the total area under the curve. We therefore conclude that the relative frequency is about 0.12 for data values greater than 18 days, which means that about 12% of births are more than 18 days late. Altogether, we see that if we add those 18 plus 12, because we had the 18 over here plus the 12 over here, it means we have 30% of all births are either more than 14 days early or more than 18 days late. Well, that's a third of our births. That's a significant number. Relative frequencies and normal distribution. The area that lies under the normal distribution curve corresponding to a range of values on the horizontal axis is the relative frequency of those values. Because the total relative frequency must be 1 or 100%, The total area under the normal distribution curve must equal 1. So we've talked about this a couple of times. This is something you should probably know. Example 2. Looking again at the normal distribution in the previous figure, estimate the percentage of births occurring between 0 and 60 days after the due date, and then estimate the percentage of births occurring between 14 days before and 14 days after the due date. So we're just doing an estimation. So you're just kind of looking at it and figuring it out. So about half of the total area under the curve lies in the region between 0 and 60 days. So between 0 and 60 days, so if we kind of cut it in half because it's symmetric, about half of it lies here and half of it lies here. This means about 50% of the births in the sample occur between 0 and 60 days after the due date. The figure shows about 18% of the births occur more than 14 days before the due date. Because the distribution is symmetric, that means about 18% must also occur more than 14 days after the due date. Therefore, a total of 18 plus 18 equals 36% of births occur either more than 14 days before or more than 14 days after the due date. And we're going off of the information that they gave us. The question asked about the remaining region, that is the region between 14 days before and 14 days after the due date. We conclude that this region must represent the whole 100% minus the 36 that occurs on the 14 days and 14 before and after. We'll get a 64% of the births occur within the 2-week period before and after the due date. When can we expect a normal distribution? Well, we can better appreciate the importance of the normal distribution if we understand why it is so common. Consider a human characteristic such as height, which closely approximates a normal distribution. Most men or women have heights clustered near the mean height for their sex. So a data set of heights has a peak at the mean height. But as we consider heights increasingly far from the mean on either side, we find fewer and fewer people. This tailing off of heights far from the mean produces the two tails of the normal distribution. On a deeper level, any quantity that is influenced by many factors is likely to follow a normal distribution. Adult heights are the result of many genetic and environmental factors. Scores on SAT tests or IQ tests tend to be normally distributed because each test score is determined from many individual test questions. Sports statistics such as batting averages tend to be normally distributed because they involve many people with many different levels of skill. More generally, we can expect a data set to have a nearly normal distribution if it meets the conditions listed below. A data set that satisfies the following 4 criteria is likely to have a nearly normal distribution. Most data values are clustered near the mean, giving the distribution a well-defined single peak. Data values are spread evenly around the mean, making the distribution symmetric. And larger deviations from the mean become increasingly rare, producing the tapering tails of the distribution. And individual data values result from a combination of many different factors such as genetic and environmental factors. Which of the following variables would you expect to have a normal or nearly normal distribution? Okay, scores on a very easy test. Well, tests have a maximum possible scores, 100%, that limits the size of the data values. If the test is very easy, the mean will be high and many scores will be near the maximum. The fewer lower scores can be spread out well below the mean. We therefore expect the distribution to be left skewed and not normal. So that means you'd have a tail going off to the left side. Foot lengths of a random sample of adult women. Foot length is a woman is a foot length is a human trait determined by many genetic and environmental factors. We therefore expect lengths of women's feet to cluster near a mean and become less common farther from the mean, giving the distribution a bell shape. We conclude that women's foot lengths should have a nearly normal distribution because you'll probably have a few small ones and you'll have a few large ones, but the average will fall somewhere in that middle in the curve. IQ scores of adults. IQ scores are measured with standard tests. The scores tend to center around 100, and scores become less common farther from the mean of 100. Also, IQ scores are a measure of intelligence, and that is a trait determined by many genetic and environmental factors. We therefore expect IQ scores to have a normal distribution.